Here at Electronica 2022, we're at the Rohde Schwarz stand to look at some new and innovative oscilloscopes, discover how they do double pulse testing for wide bandgap MOSFETs, and also what's behind quantum computing. Hi Jithu, it's great to see you here at the Rohde Schwarz stand here at Electronica 2022. We have chatted before in the past about the new MXO4 series oscilloscope, and the nice thing is it's here on display.
It's here, exactly, yes. So it's one of our highlights for Electronica 2022, that we've now have this new generation of oscilloscopes in our portfolio, and mainly for the 4000 class or 4 series class of scopes. Goes from 200 megahertz up to 1.5 gigahertz, and it has some very new and exciting attributes that I'd like to talk about and share how this makes a difference to engineers when it comes to testing, when it comes to verifying their devices.
Now I understand that obviously in the upper class range of your oscilloscopes, a lot of time and energy is spent on developing ASICs to really enable all that electronics and that measurement capability to be integrated and the performance to be achieved that Rohde Schwarz is known for.
Yeah.
But you've taken some of that and put it in here. How have you done that and what's inside?
Absolutely. So as you said, 10 years ago, when we launched our first RTO oscilloscopes, we invested heavily into ASIC technology, building that to be the performance core for the instrument. And this was our vision, that over time we would then design new ASICs that also come to the lower end of the portfolio. And this is our new ASIC that we've developed now. So it's a traditional ASIC, if you like, that has lots of transistor gates and so on and things, but mainly it can process data, about 200 gigabits of data per second. So that's a lot of number crunching. To give you an idea, what that means is like if you take a Netflix movie, this ASIC can crunch 8 of those Netflix movies in a second.
Wow.
So a lot of processing power just in that instrument. And why do we need this? It's mainly to generate lots of signals on the screen so that you get to what you're trying to look for much faster, much quicker, and all that measurement data is all done in the ASIC so that we have a much faster performance. The new ASIC, we're calling it the MXO EP, EP standing for eXtreme Performance. And as I said, this is our first generation of oscilloscopes that are going to be using this ASIC, and there's a lot more to come.
Now, as a user of oscilloscopes, when you're trying to find an issue, trying to find a problem, typically it's not the signal that's on the screen that you're looking for, it's the little glitches that come up. And most oscilloscopes, as are typical oscilloscopes nowadays, stick with like an 8-bit ADC. What sort of depth of resolution do you have on this one?
Yep, that's a good point. So we also invested into the front-end design of the scope itself. So yes, it's a test and measurement instrument, so we have to be somehow better than what you're testing for. So we have a 12-bit ADC now on this platform. So it's our first 12-bit ADC scope in our portfolio, and it helps because you get that more resolution, as you say, to both see those signals and so on, and to rectify those small glitches, small anomalies that sometimes is buried in the noise, let's say. And we took it a step further as well to not only look at 12 bits, you can have things like HD mode that gives you 18 bits of resolution for maybe slower bandwidth signals or so on, so that you have more resolution, especially down when it comes to power applications, where you don't maybe need the high frequency content, but more the low frequency content, but require more resolution. We also invested into digital trigger, so it's okay to rectify these small anomalies and so on, but even more equally important to trigger on these anomalies and things. So allowing digital trigger helps us to actually pinpoint and trigger on these tiny glitches, tiny anomalies, so that people can understand how frequent this is, or get a stable waveform just to start making measurements and things. So
Now, as we're looking at the screen of an oscilloscope and we're looking for those glitches, those anomalies, also so like in serial communication, sometimes the screen's just not responsive enough. we don't even see that the glitch has occurred. Have you been able to resolve that with this platform?
Yes, so with the ASIC that we mentioned before, I said it's a big performance core for the instrument, but it's largely also responsible for how fast we can actually get the data, do all our mathematic calculations on it, and then put it into display. So we call it like a waveform update rate, or like a refresh rate or so on, and things that you can hear on displays. But this essentially means that how fast we can trigger, capture, and put it onto the screen. And for the MXO, we have the world's fastest update rate now, with about 4.5 million waveforms per second. About 10 years ago, we came out with the RTO, which had 1 million waveforms per second. Now today we have 4.5. So that, as you say, when people are looking for these events that maybe occur very infrequently, or they want to have the assurance that they're capturing all the pulses that they need, all the information that they need, and not missing any information, this really helps in capturing all those data, all those signals very quickly, and keeping all of that information on the screen for the user.
Now, the capabilities of such oscilloscopes has grown enormously, and I think one of the challenges lots of people have is how to actually set them up and configure them. We've got the traditional rubber buttons and knobs, which I think sort of everybody keeps because that's the way we interact with an oscilloscope. But then, what about the user interface to access the other functionality?
Yep. So, as you say on the scope, you can see we have the dedicated knobs and dials that people are used to, because that's people still like to change different things and so on. But we now have a 13.3-inch touchscreen, a full HD resolution touchscreen that people can interact with and so forth. So everything on the instrument, we try to maximize the waveform area, if you may, so that you still get all your information. So you have all the channel information there, what the scope is actually triggering, what the acquisition is doing, all of that is just there. But all the menu and so on is just docked down here so that you find everything that you require. And it's always on these tabular formats. So you have this dialog box that comes up, and we made it in a box design so that in the past, when you use touchscreens and so on, we found users really difficult to really pinpoint on that single digit and so on to change a parameter. Now you can have this box where you can click and you can change any parameter and so on real quickly. So it's easier to get to and so forth. And what I personally really like on the UI is the new search function. So there's been numerous amount of times where there's this one function that you very rarely use, and it's always a pain to find which menu this is in. So just like a mobile phone and so on and things, if you're used to, you can then just go into the search dial, and then let's say you want to find something like persistence or so on, you just start typing that in, and you get a selection of possible keywords, let's say, and then there you go, that's my persistence, and I can go directly into that menu. Nice and simple, nice and easy. So we try to work a lot on the UI to make it easy, simple to navigate, and also get to the signals that they're most interested in to find out what's actually going on to my board, rather than actually learning a new instrument as well.
Now there's a whole host of advanced technology in here and measurement capability. What sort of price range or price class does this type of oscilloscope come into?
Yep, so this with the MXO4, as I said, it starts at 200 megahertz, and the starting price is about 7,600 euros. So still an affordable class, even though we have lots of these new capabilities and so on, still in that 4,000 class price range, let's say. And then from that you can go up to, depending on options and so on and things that you do, around about 18 to 19,000 euros. So a lot of capability in there for engineers who want to look at the signals and care about the signal quality and so on that they're trying to measure and find.
Well, thanks very much for guiding us through the MXO4 series. It's great to see it here at the show, working and getting some insights here as to how you actually can use it and the capabilities that it can really deliver.
Yeah, perfect. Thanks a lot, Stuart.
Good. So Florian, lovely to meet you here at Electronica 2022. We're here at the Rohde Schwarz stand because Zurich Instruments is part of the RS group, and what you're displaying today for us is a quantum controller for a quantum computer. I just wanted to start by asking, where are we in quantum computing? Are we in a position to run applications, or are we still figuring out how to make quantum computers?
Yeah, so it's really the second. We're in the process of figuring out how can we control a quantum processor with multiple qubits, how can we do operations on it, and how can we scale it up to make it more useful, and at some point also solve real world problems. So at the moment we're really in the process of improving the qubits, and yeah, so it's more in a research stage.
So a quantum computer is obviously made up of lots of parts. We've got the processor where the qubits actually exist and is cryogenically cooled, I think, to an exceptionally low temperature. Mm-hmm. What do I need around that then to be able to put data in and execute a calculation and get the data out again?
Mm-hmm. Yeah, so in first place you of course need the qubit processor itself, which is a chip that lives inside a cryostat at very low temperature, as you say. And in that cryostat you have the cabling, the wiring, and other components, electronic components like amplifiers. And then outside of the fridge you need the control electronics, room temperature control electronics, just like here the qubit controller. And with this control electronics you send in pulses to control the state of the qubit, and you also send in pulses to read out the state of the qubit. So these are the parts that you need. Yeah.
Now, when we think of a traditional CPU, a traditional processor, typically we're running at the clock speed of the oscillator, and in one cycle I will push a data into a register, a calculation will normally occur, and then a clock cycle or more later I can read that data out. Is that the same process that happens here with the quantum qubit controller? Mm-hmm.
Yeah, so the equivalent to it would be the coherence time of the qubit, which is the time in which the fragile quantum state is still preserved and the information is there. And after that time, the information that you encoded in your qubit will be lost. This is because the quantum states will just decay. And so every operation that you want to do has to happen within this coherence time, and this is basically limiting or defining you a sort of equivalent to a clock cycle of a classical processor.
So the qubit controller in the demonstration you have here at the stand today,
yeah.
This is outputting the data, as it were, the setting that we want for the qubit, and then it's actually reading that process back, the result of the qubit back out again. How is this demonstration set up, and what do we see here on the oscilloscope?
Yeah, so on the one hand we have the qubit controller, which sends out all the pulses that we need, and then we have an oscilloscope here which can display us the pulses, and in this way we can analyze the spectrum of the pulses and the timing of the pulses. And so what we see here now is two channels of the signal generator part of the qubit controller, which sends out pulses to generate and to prepare a certain qubit state, but also do a calculation on the qubit. And this is the yellow and the green pulse that we see here. And by varying or defining the length, the amplitude, and the phase of these pulses, we can prepare certain states and do calculations on the qubit. So this is the one part that we see. And the second part is how to read out the qubit and how to retrieve the information after you did your calculation. And this is done by coupling the qubit to a resonator, which also lives on the chip at low temperature. And here we mimic it with this cavity, which is just for a tabletop demonstration. And here what we do is we take the quantum analyzer channel from the qubit controller, which is used for the readout. So what we do is we send a pulse close to the resonance frequency of the resonator, and then here now we just display it on the oscilloscope, which is the orange pulse. But in a real experiment, we would send it back to the instrument and then measure amplitude and phase of this pulse. And this allows us to derive the state of the qubit that we had, because the qubit state will change the resonance frequency of this resonator, and this will result in an amplitude and phase shift of the readout of probe pulse.
So when a qubit is read, I would be expecting to have a 1 or 0 result, but how does that signal look that comes out of the qubit? Am I also seeing a logical pulse, as it were, like a traditional processor, or is it more of a frequency, amplitude, phase combination?
Yeah, it is the second one. So it's really like this pulse that you see here, and then you get then this pulse looks slightly different for the logical 0 and the logical 1 state of the qubit. And then this will be in your amplitude versus phase space in 2 dimensions. It will give you 1 point for the 1 qubit state and another point for the other qubit's logic state. And then you have to distinguish between these two. So you really have to convert these amplitude and phase values, which are somewhat just arbitrary or given by the setup itself. And you have to then convert it into a 0 and 1, basically. And this is also done on this qubit controller, actually. So it reads out the phase and amplitude of the pulse, and then you can convert it here. We can see it. We have here the signal analysis chain of the qubit controller, and here we do the integration. We measure phase and amplitude, and then we can do a thresholding in this 2-dimensional space. And yeah, that's how we can then get this logical 0 and 1 of the qubits.
Well, I really appreciate you taking the time to go into so much depth and explain this important and critical part of a quantum computer, and we wish you all the success for the continued development of quantum computing.
Thank you for stopping by.
So hi there, Jens. Lovely to see you here at Electronica 2022. You're from PE Systems. What's your relationship to Rohde Schwarz?
So we're a partner company of Rohde Schwarz, and we develop solutions for power electronic testing together. And this is our first setup, a double pulse tester. So all the measurement equipment, the laboratory source is coming from Rohde Schwarz, and the setup and the software for the automation is designed by us.
So what are the capabilities of this double pulse testing system here?
So with this configuration we can test devices up to 1.5 kV and up to 3.6 kiloamps. And what we have right here is the road pack, so a half-bridge module for automotive applications, which is tested here up to roughly, so it's a 1.2 kV module, and we test it up to 800 volts in the fair.
Yeah. So one of the interesting things in the power switching market is obviously this transition from silicon to silicon carbide and GaN. Is this ready also? Is this a silicon carbide setup here?
Yeah, so this is for silicon carbide. We have different options to change the properties of the system. We can exchange the capacitor bank, exchange the module fixture. So we can easily adapt it to different demands, and we're also working on solutions for small fast switching GaN devices.
What's the purpose of the double pulse test? Is this something that every device has to be tested for? Is it more during the research and development phase to evaluate different power devices?
Good question. So we have different customers. So on the one hand, of course, people who develop modules want to test them to fully characterize their modules, but we also have people who are working in applications and want to test the modules in their applications, so with their loads, and as close to application as possible. And this is also possible.
And obviously we're transitioning at the minute from silicon devices to wide bandgap. What are the challenges with the double pulse test and the response of wide bandgap devices that we didn't see with silicon?
I think the major issue is that we have to consider many high frequency effects, and the biggest challenge is to measure the current with high bandwidth but without disturbing the setup too much. And here there are many ideas, but the perfect solution is not there yet, I would say.
Well, thanks for guiding us through the setup here.
You're welcome.
We'll wish you a great show here today.
Thank you.
So hi Ian, great to see you here with the PE system setup. We've just talked and found out how the hardware is implemented for the testing, but obviously there's some software required as well to execute the test and gather the data, and you're going to take us through how that works.
Of course, I mean the software is where I think the value is really added to the client. It will become apparent now. Firstly, if you want to make a measurement, you want to connect your setup. We have saved our current setup under a setup called electronica, but of course you can just call it whatever you want in your lab. After I've connected, you can see here is your page where you manage your devices. So in this corner we have currently the new Rohde Schwarz MX04 connected. But as you can see, all the other many Rohde Schwarz oscilloscopes there are as well implemented already. That's not a problem. Same goes for the waveform generator, high voltage power supply, gate driver, the gate driver power supply, and of course the important thing, the star of the show, which is the model we are testing, the device under test. Currently, as my colleague already mentioned, we have the road pack. So I've just selected the road pack from the loaded devices already into the software. Adding a new device is also very, very easy. So now, after I'm happy that all my devices have connected and I've selected the right ones, I can go to the measurement page, which is where I'm going to actually do some measurements. As I said earlier, I think the real value to the client comes from the software, and one really great example from this is if you see here, all the settings and everything, all the tests are obviously being saved and recorded, and the traceability thereof is fantastic. So if you are doing tests over weeks, a long time, all the data is saved and you can go back, see who's done tests, when's done them, under what conditions, has your probes, if something is off, has your probes changed, maybe something doesn't work with a probe or something. All this can of course then be looked at if you have got this traceability. So you can export it in different formats. So just wanted to show that. This is where we define what tests. So first I can sweep and do tests on various temperatures, of course. Voltages as well, I can select various voltages. We'll just do a test, let's say 600 volts. And we'll step through different currents. Let's start at 200 and end at 600 amps. Different settings for the gate driver is also possible. So gate on resistance, off and on voltage, all of that. So after I've selected all the settings and all the points that I want to measure our device at, I can actually start the tests. So right now the oscilloscope, the oscilloscope has just recorded a single test that has happened. And there we go, the data has come through. The oscilloscope has now sent the raw data to the computer. You can see the graphs on the screen here. And the computer has also done all the calculations needed. So there's an automatic D-skew, and it has done all the important calculations that is of interest to us. Yes, so the 600 volt, 200 amp, 300 amp and 400 amp test has already successfully completed in the short time. Another important thing is, if you look here, there's a typical graph you can find on a data sheet of such a module, which shows the current and the switching energy on the two different axes.
So I was going to ask, who in the electronics industry is sort of interested in this level and depth of data for every individual switching device that they, because obviously the semiconductor industry is promising this performance in their data sheet, so who's checking it?
Well, there's two different types of customers. Firstly is the people that the manufacturers of these devices themselves.
Yeah.
Of course, they want to generate data sheets as reliable and as accurate as possible for their clients and for the user. So it's a really important factor for them. And secondly is the system integrators. What they do is they want to firstly verify the data sheets, make sure that within maybe maybe the data sheet doesn't cover what they want to do, or maybe they don't trust the data sheet. So they want to verify it. And also the second thing is very, very important is, if you have your system already built, maybe you want to optimize something on the system, you can also do it on our test. So you bring in your whole system with your load, your extra capacitors on the devices and everything, and you test it within the setup and see maybe if your own system can be optimized instead of just testing a module with our optimized setup.
Well, that's great. Thank you for taking us and guiding us through that testing process, and have a great show.
Yeah, thank you very much.